Hello and welcome to Deep Learning with Pytorch Lesson 9. Today we are going to be finishing up chapter 5. We're doing the second half of chapter 5. It should go pretty quick. We're going to hit these two lines of code, autograd and optimizers. The big things to look out for in the rest of this section is grad memory, where we are going to be using the tensors to store the gradient of different tensors as we perform operations on them. We're going to do a little bit of optimizers and learning about the optimizers. We're going to be talking about training and validation of models, what a training set is, what a validation set is, and that will lead directly into what is called overtraining. And overtraining is very important. It's important that we understand how that works, and then we will be able to hopefully prevent it in practice, because it's a very common error to occur, and we don't want that. So let me go to the book here, and I'll just start. This is where we are starting. This is where we finished up last time. So we're sticking with the same data set, which is kind of a strange data set. It's very small, but it's okay. That's what they chose to use. So we'll restart this to clear the output. We're going to go ahead and run this line of code here. We're just importing our different modules. We're importing numpy as np, and we're importing torch, setting our print options edge items equals 2. That's fine. We're not going to be printing a lot of stuff in this lesson. Okay, so last time we did normalize the T sub u, which is the T sub unknown temperatures, which is it ended up being Fahrenheit. We're normalizing that. Normalization is kind of a funny word for that, because we're not really using a typical normalization formula. We're multiplying it by 0.1. We're reducing it by 1 order of magnitude. That puts it in a closer range to the T sub c. There are other ways to normalize it, but just remember, any method you use to normalize it has to be reused to normalize new data, and also has to be used when in regards to your results. So if you do a very complex one, it's not that hard. You could just recode it, the inverse of that, to transition the numbers back to their original form if need be. Okay, so we did this last time. The model of it's a linear model. Weight times T sub u plus b. The w is the slope, and the b is your constant. The w would also be referred to as the weight, the b, the bias. Okay, so now we need a loss function for that. We're just going to say the difference between the two squared. So squared difference mean. So now we have a loss function and we have a model function. Now what we did last time was we took the derivatives in order to determine the gradient of these functions, because that's what the derivative of a function does. But that's all well and good in a calculus class, but sometimes your functions are too complex to be able to take the derivative of them and have an explicitly defined derivative. Luckily, we do have computers on our side here, so we can run these two lines of code, and when we say params equals the torch tensor, we could say requires grad equals true. And what this will do is track the gradient of these matrices, or tensors, as we go through and perform different operations on the tensors. So we can run that. Now, this is how we call the gradient params.grad, and that will give us the gradient. So right now we're going to say, is it none? It's like asking a question. Is it none? Question mark. Yes, it is none. It gives us a Boolean value. If we take this is none out, we just don't. It just doesn't list anything. So how did they have that? Oh, is none with a capital N only is the way to do that. And when you run that, you get true. It's a Boolean value. It's saying, yeah, there's nothing in there. There's nothing in the params.grad. Now, let's go ahead and mess with our params tensor. We're going to put the loss function on our model function on our T sub u and our different params. We haven't defined the params, but I guess that's okay. Oh, yes, we did. Here they are. 1 and 0. Our W is a 1. Our bias is a 0. We run that. We get a gradient. So if you remember from the first one, we had these crazy... Here's the loss function. Okay, didn't we have like a grad... Loss rate of change is what we called it. So that's what we were getting here. Now it's just doing it for us. So that's all it is. When you have this, you're just tracking your gradient. That's all. So very useful function. If params is not none, params grad equals 0. Okay. So if we were to say A, not A, let's say DD, that deletes it. Let's say B, and now we add this params dot grad 0. Why did this happen? It just was this, right? But this line of code is very simple to understand. Sometimes code is difficult to understand. Sometimes it's easy. This one's easy. If params.grad is not none, so double negative there, is not none. So if there's a value in there, like this, it's not none, it's 4082, then make it 0. That's all we're doing. If it isn't 0, make it 0. So now it's 0. Very simple line of code to understand. This dot 0 underscore parentheses just sets that tensor equal to 0. So now let's define the training loop, the number of epochs, the learning rate, the params. So we're defining a function here, and this function depends upon epochs, learning rate, params, TU, and TC. All right, so for epoch and range, if it's not none, set it to 0. Why are we doing that? Why are we setting our parameters equal to 0 every time? Because we want a new gradient. We want, after each iteration, that gradient changes. So we want to know the most recent gradient and utilize that gradient. We're going to utilize that gradient in order to optimize our loss function. So we're taking that data. That gradient is the rate of change, remember? So we're taking that rate of change and utilizing it to determine how fast we change our weights and biases in order to obtain the best possible solution. Okay, so here we're just saying if it's not none, set it to 0. Easy line of code. We just did it here. We understand that. TP equals our model of this and our params. This is just a fancy way of calling the parameters. Sometimes there's more than 2. In this case, there's only 2. The loss function equals that. Loss backward. So let me see. I found something good in here on the backward gradient, essentially. Calling backward will lead the derivatives to accumulate at leaf nodes. We need to 0 the gradient explicitly after using it for parameters updates. So we just talked about that. That's the grad 0 one. And yeah, so this is just what's called back propagation. And this we'll get into in a little bit here. It does say this in the book. It says, the means within the width block, the Pytorch autograd mechanism should look away. I found it easier. The book didn't describe this one that well. Basically, all this does, torch.nograd impacts the autograd engine and deactivates it. It will reduce memory usage and speed up computations, but you won't be able to back propagate, which you don't want in an eval script. That's the best answer for that. So we're turning off the grad. That's all we're doing. So we set grad somewhere around here. Requires grad equals true. Now we're just turning that off. Okay, so we'll run this, and we basically get we define our function here, and now we're going to run our function. We're going to say, let's do 5,000 epochs. Remember, this statement here is just a printing statement. It's what, when we run it, what we want it to print. And this is how we run it. We're saying requires grad equals true, learning rate equals 1e to the negative 2. And boom. 5.3, negative 17. I'm pretty sure we got something like that last time. So that pretty much settles up. We just made our life easier in this entire thing of coding. All we really learned here is that requires grad equals true is good, and it makes it so that we do not have to explicitly define the derivative. Okay, now we can run, go to optimizers. And now optimizers are listed in the book here. Here's a definition of the optimizers. You can go through that. But here's all of the various optimizers listed here. Some of the more used ones. Some of the more common ones. Wow. Okay, some of the more common ones are atom and SGD. So we'll go ahead and run this, and then we can run this. We're doing the same thing, and we'll see the benefit of using atom when we use these optimizer functions. So let me go ahead and restart and clear output actually though. So run. We just did the same thing. We defined modeled, we defined loss function. Let's get all of our optimizer functions that we can use at any point. Now we're defining our optimizer here as SGD. We're defining a very small learning rate, and we can just model it right like that. No problem. All right, now we will use another SGD, and we're going to make our learning rate a little larger here. So now we're able to kind of play with these things a lot faster. Okay. And we get these. So we haven't really done any iterations yet. We're just doing it right off the bat. Now we're going to do something with iterations because we're defining a training loop with a number of epochs, optimizer, params, TU, TC, everything. So let's define this function. Our optimizer, 0 grad. We're zeroing out the gradient there, I guess we don't define the optimizer in this one, but we define it here, and optimizer equals optimizer. So if optimizer equals optimizer, it equals this, which is optim.sgd. SGD is standard gradient. Oh, sorry, no, it's not standard. It's stochastic gradient descent. Run that, and boom, we get a good result. Now, remember, we are still setting TU equal to TUN. So we're still doing that normalization technique where we multiplied it by 0.1. Now we're going to use the most commonly used optimizer function, which is atom. We're using a very large learning rate. So we're doing a lot of things wrong here. We're using a really big learning rate. We're not normalizing the input space. We're not multiplying it by 0.1. We're just saying T sub U equals T sub U. And let's see how well we do. After just 2,000 epochs, we're getting about the same results there. The gradient function performed just fine. And you can see in the output space, it's 0.5. And this one is 5. So they never re-multiply this by 10 because initially you multiply it by 0.1. So in that case, you either need to set your input values and multiply them by 0.1 or do it in the output range. Just something to be aware of. So now we're talking about indices here. This isn't too particularly important. All that we're doing is we're kind of randomly shuffling our indices here. And we're talking about training indexes and validation indexes. So we're doing a random shuffle here, and this one's only getting 2 and 3. So we jumbled all these numbers up, and we took 2 out. Okay? And that's because it's 20%. We took 20% of them out, which is only 2. So our validation set is extremely small because our data set is extremely small. We'll go ahead and run that. Now we're just doing some bookkeeping here. Train T sub U, train T sub C equals the train indices, and val indices are these ones, which are our validation. So we need to see this in the book to fully understand what a training set and what a validation set are. They have this kind of silly picture. I don't know what it is. It looks like some stuff going into some sacks with a rope or something here, but basically it still does get the point across, which is the data producing process. We have our data and we split it normally into an 80-20 shuffle. 80% will go to the training set, 20% will go to the validation set. We optimize our parameters, training. We train our parameters with the training set. And then we test on our validation set, and that is how we evaluate our performance. So our model never sees this data until it's time to test it. It's a good way to test it. And this is an example of a model that is well trained, and this is an example of a model that is overtrained. So in this case, we never looked at that parameter where we took some of the data out, like maybe there's a dot here, a dot here, a dot here. None of those will be a good match because we didn't train with those. We just overtrained on the data that we had. We trained it till it fit every single dot, and we don't want that. We want the relationship of it. And I think that's this is how you would view that. So if we go back to our code here, I think we do, if we run a few more lines here. So this is an example of us tracking the training loss and the validation loss. And if you're going to take anything away from this, take away the fact that you want your training loss to go down and you want your validation loss to go down. If they're both going down, that's good. If your training loss is going up and your validation loss is going up, that's bad. There's an example of that right here. And not really up, but it's staying the same. That just means you're not doing anything. Your loss is staying the same. Your model is doing nothing. If they both go down, that's the best. Okay, they're both going down at the same rate, and they're both around the same value. That's the best. That's the best you can do. Here's one it's also okay, where the blue is your training loss, and the red is your validation loss. It's going down, but it's just training a little bit better on your training data. But this is going down too, so that's still okay, and you can still continue to train with these. This is bad. This is overtraining. B is overtraining. Training loss decreases while validation loss increases. Overfitting. Overfitting, overtraining, same thing. So that's the main thing to take away. If they're both going down, you're doing good. If they're not, you got problems, and you need to learn more about this stuff. So now we can do a calc forward, and that's really just about it. I'll see you guys in the next section. That is the end of chapter 5. Thank you.